This video is a walkthrough of our first functional programming lab. Its purpose is to help you if you get stuck while working through the lab in your groups. That means you don't need to watch this video before class. All you need to do before the lab day is make sure that you have Racket installed on your computer and that you can run the Dr. Racket development environment. To install Racket, you can go to racketlang.org and the download page, and then you can select the appropriate distribution for your computer, Mac or Windows or Linux, and you should pick the 64-bit version. Once that's installed, you want to run Dr. Racket and confirm that you can get to this screen. From here, you should be able to work through the lab exercises in your group. And so at this point, I expect you to stop the video and only come back if you get stuck. The rest of this video will be me working through the lab exercises, and so if you do get stuck at some point, you should go through the video to the point where I'm doing that same part and see how I got past your sticking point. So, we're going to be doing functional programming in Racket. Racket is a dialect of Lisp, and Lisp is one of the oldest families of programming languages that's still in active use today. Lisp and Racket use a functional programming paradigm, and we'll see much more about what that means over the course of this activity and the rest of our labs this semester. We've gotten Dr. Racket running, and now we can use the read-eval-print loop in the bottom half of the Racket window to execute Racket code. We can evaluate expressions like strings and numbers, but if we try to add two numbers in the way that we might normally expect, it doesn't give us the usual result. The reason is that this read-eval-print loop is expecting us to give a Racket expression in parentheses. And so if I want to add 2 plus 2, then the first thing I put is the operation, and then I put the arguments to that operation. And so this expression performs the operation plus on the inputs 2 and 2 and evaluates to 4. Similarly, I can do other sorts of math. I can do a division operation with inputs 5 and 2, and that will compute 5 divided by 2. And this gave us a rational number as the output. So Racket can do exact math with rational numbers, which can be very handy for a lot of discrete math things. And we can also do modular arithmetic, or we can do floating point division. And if we want to throw away the remainder, like normal integer division would, we can explicitly call a function like floor on the result of our division. And so here we evaluated the division operator on inputs 5 and 2, which we know gives the rational output 2.5, but then we gave the 2.5 result to the floor operator, which output the integer 2. In addition to rational numbers, Racket has a built-in representation of complex numbers. We can use the square root operator on input -1 to get ourselves a complex number. And we can also specify complex numbers directly. And we can give complex numbers as inputs to other operations. So I can do the multiply operator on -3 and the complex number 1 plus 2i. And Racket knows how to do that computation. On the other hand, the floor operator that we've seen would not work on a complex number, because floor specifically expects an input of type real, and we gave it an input that was not a real number, and so it didn't know what to do and gave us an exception. This exception hints at Another type of operator we can use, there are operators for checking various types and properties of numerical values. The real operator will tell us whether its argument is a real number. So 2 is a real number. The string hello is not a real number, and so it's outputting true or false as the result, and #t or #f are the Racket representations of true and false. There are lots of other Boolean operators, most of the ones you would expect from any other programming language, and they work in the Racket prefix operator style. So we can ask, are two numbers equal with the equal operator? We can ask if a number is less than another or greater than or equal to another. And it knows that, for example, the integer 2 is equal to the complex number 2.0 plus 0i. And in fact, 2.0 plus 0i reduces to a real number. Of note here, the equal sign is an operator checking for equality. In many programming languages you might be used to, this would be done with double equals, whereas single equals would be used for assignment. Assignment is more cumbersome in Racket, and that is deliberate because in functional programming we use assignment statements much, much less than we do in imperative programming. And so the equals operator is just for checking equality, and we'll see define and let expressions for assigning values. A define expression has two arguments, one of which is the name we want to define, and the other is the value we want to bind to that name. So if we run this and then evaluate the name x, x is now 2.5. Also, with all of these operators that give a Boolean output, we can use those Booleans for conditional statements. So we can do if then else with an if expression. We could check whether x is an integer with the integer question mark operator. And we can also have an if expression that depends on the result of that check. An if expression has three parts after the if. There's the condition, followed by the then case, followed by the else case. And putting all of that on one line would get very hard to read, so you should, for your if statements, generally put a new line after the condition, and Racket will nicely line you up with that condition for your then clause and your else clause, and then you can close out the parentheses on your if statement, and I like to tab that back to line up with the start of the if expression. So if x is an integer, we could compute floor of x plus 2, or we could just compute plus x 3 in the case that it's not an integer. And here, since x was 2.5, which is not an integer, the if will be false, and so we'll go to the else case, and this whole if expression evaluated to x plus 3, which is 5.5. If we were to do this again, but first define x to be 2.0, now we could repeat this. So what happened here is that even though we assigned a floating point value, it knows that 2.0 is an integer, and so that triggered the if case, and it computed x plus 2, but the floor operator that we gave that result x plus 2 into will return the same type of thing that it was given. So we gave a floating point data type 2.0 plus 2, and it gave us back the floor of 4.0, which is just 4.0. So it didn't convert that to an integer, it just rounded it down. In addition to if-then-else statements, we can use a conditional expression, which allows us to specify several if-then cases in a single expression. So rather than nesting a whole bunch of ifs inside each other, we could have one statement that allows us to do multiple condition checks. So here we have a condition where first we're saying if x is less than -1, or if it's less than 0, or if it's equal to 0, or if it's greater than 0, or if it's greater than 1. So we have 5 different possible cases, and in each case we're displaying. Display is how you print things in Racket. So we will display a different result based on which of these conditions triggers. So let's copy and paste. Note the change in color here. The purple output is the result of printing with a display expression, whereas the blue outputs that we got before were just the value that was produced by the expression. So in this conditional statement, since the value of x was 2.0, we know that the first 3 conditions will all evaluate to false, and the last 2 will evaluate to true. And so what's happened here is that the first of the conditions to evaluate to true was triggered, and then the condition expression was done, so we didn't get a chance to print out that x is greater than 1. As soon as we saw that x was greater than 0, we produced the output x greater than 0. If we wanted our 5 cases to be all mutually exclusive, we would need to change the negative and positive checks to ones that were an and of checking greater than 0 and less than 1, or greater than -1 and less than 0. So we could use an and operator on these 2 different Boolean checks. And operators like and behave the way we would expect based on their truth tables. So to do some actual programming, we'd like to be able to define functions. In Racket, this is done with a Lambda expression. So the lambda says we are defining a function, and then the next piece of the expression is the collection of arguments to the function. So we could have a 1-argument function or a 2-argument function, or more. And then the next expression is the body of the function. And so here I could do plus x1. And so this would be a function that takes 1 argument x and outputs x plus 1. If I run this, then the thing that is returned is a function. And so in Racket, as a functional programming language, functions are data objects in the program. That means that we can have functions that are returned by expressions, like we saw here, but we can also have a function that is an input to another expression, or we can have a function that we give names to or pass around throughout our program. So if we want to actually use this function, well, here we have an expression that creates a function, and so now this could be the first element of another expression. We could put an open paren, and then this is the first element, and since it operates on one argument, we could give one argument, close parentheses, and now the procedure that is produced by this lambda expression will be applied to the argument 5. But if we're programming, we generally want to define a function and give it a name so that we can use that function multiple times. And we can use a define expression, just like we bound the name x to a numerical value, we could bind a name for the function to the procedure that is returned by the lambda expression. So we can define the name incr for our function that is incrementing its input. And here again, we shouldn't try to put everything on one line, so we'll make a new line. And now the thing that we are defining is our lambda function, and that has two components, the input and the body, which we'll come back to. And then our define statement needs to be closed at the bottom. And so now our lambda, we should put a new line here to separate the body of the function from the arguments. And here the body of the function was plus x1 to increment x. And for clarity, we can put this close parenthesis for the lambda at the same level of indentation. And so now we are indicating that lambda is this function, and it is now being bound to the name increment. And so now if we do that, incr refers to a procedure, and we can call that procedure by evaluating the expression incr space the argument we want to pass to this function. And so incrementing 2 gives us 3. Functions can have any number of inputs, so let's define a 2-argument function. And we take 2 arguments this time, so we'll call them x and y. And now we want to evaluate the absolute difference between x and y. So we'll do the abs, and we will apply the abs operator to the result of the subtraction operator evaluated on x and y. So our function is taking arguments x and y, and then it is evaluating x minus y, and then evaluating the absolute value of that. And so that is our procedure, and we are binding that procedure to the name absdiff. And so now when we run this, we now have a function called absdiff, and we can evaluate that procedure by giving 2 arguments to it. And so it did subtraction, -1 minus 4, it got -5, and then computed the absolute value of that and evaluated to 5. So we've been doing everything so far in the read eval print loop portion of Dr. Racket, but we also have this top half of the window, which is the definitions panel. And this is where we'll actually write most of the code, because here we can much more easily do multi-line definitions, and we can save our files, and then we can run the whole thing at once to define all of our functions that we can then use in the REPL below. So let's define a function for doubling. I'll paste that in up here, and my pasting gave me some bad indentation, so let's fix that. Now things are lined up to clearly indicate what's going on. Our function multiplies its input by 2, and we are binding that to the name double. And now if I use this run button, it will clear everything in the terminal and then execute all of the expressions in our definitions pane, and anything that we defined there will now be available in the REPL. So because the REPL got cleared, if we try to increment 2 again, that's no longer defined because we only defined it in the previous REPL session that has been cleared. But our double function that we defined up here does exist and can be called after we have run the definition pane. We can also have outputs from a program that we write in the definition pane. For example, if I did display double of 10 and then ran the definition pane, then in addition to defining our double function, it will, when it evaluates this display expression, print the output to the REPL. As you get used to functional programming, you'll probably find yourself using named variables a lot less frequently than you do in imperative programming, and that is strongly encouraged by the construction of the language. But there are definitely times when we need to save an intermediate result, and so it helps to have a local variable that we can use to do that. So let's add a new function to our definition pane. Here we will define the function f to be a lambda that takes one argument, and here will be the body of our function. And now let's close out our parentheses. And so in this function, we want a local variable y that we can use to store an intermediate output. We want to first compute x minus 10, and then we want to do a couple of different things with x minus 10, and so we want to have that value saved into the variable y. And we do that with a let expression. So a let expression takes first a binding that we want to make, and then an expression we want to evaluate under that binding. So what do I mean by binding? I mean that we're going to name the variable y. So we'll say that y is the result of evaluating x minus 10. Let's put in a new line. So here we're saying that within this let statement, the name y refers to the result of evaluating x minus 10. And so then we're going to evaluate the expression that we put in the body here, and in this expression we can use the name y to refer to whatever value we computed here. And so now we can have an if statement that depends on y. So if y is positive, we have a then and an else. And so our then could just be y, and our else could be y over 2. And so this let statement gives us a local variable, but that local variable exists only within this let statement. So let's run this, and if we try to refer to y outside, y is undefined because its scope is only this let statement, but the things that we defined up above, like f, are defined in our REPL. And so we could evaluate f on the input 25. So I need to not have parentheses around my y here. We can fix that and rerun our definition pane. And now we'll do f evaluated on input 25. And so y got bound to x minus 10, where x was 25, so y was 15. And so then y was greater than 0, and we just returned y. But if I had called f on the input 5, then x was 5, so y got bound to -5. And so now the if condition was false, and so we went into the else case and computed -5 divided by 2 and got -2.5 as our return value. So let's reason through what's going on with this definition and let statement and figure out what we should get when we print out R. Here we are defining R to be the result of a multiplication operation, and that multiply operates on M and a let statement. And so the first argument to the multiplication will be whatever this let statement evaluates to, and the second argument will be M. Within the let statement, a different local definition of M is being given, but that definition has scope only the let statement. And so the M that's outside of the let statement will have the globally defined value of 2. So we're eventually going to be setting R to be the result of the let times 2. So now let's figure out the result of the let. Well, inside we are first setting M to be 3. So for the scope of this let expression, M now has the value 3. And then we are setting N to be M times itself. So we just set M locally to be 3. And so now we're computing 3 times 3, and that gives us our value for N. And so now N evaluates to 9, and M is 3. And so those are the bound values within this let expression. And now we can evaluate the body of the let with M equal to 3 and N equal to 9. And we compute the product of those, so we compute 3 times 9. So the let evaluates to 27. And so now the overall multiplication expression evaluates to 54. So let's try this out. We'll copy and paste. Let's fix some indentation. And if we run this and print out R, we get 54. The last piece here is that in part 3 of your assignment, you'll need to be able to produce an error if the result is a bad one. And we can do that with the error expression. And the error expression just takes one argument, which is a message to be printed, and it produces an error. But we can also have a function where in the midst of that function, if we determine that an error has occurred, we can use the error expression to create an exception that will stop the execution of that function. So our example is an inverse function, which we will bind to a lambda that takes one input parameter. And then the body of our lambda will be an if statement, where we're first going to check for our error condition. So if the thing that we're trying to compute an inverse of is 0, then we would be dividing by 0. So let's produce an error. And then in the else case, where we know that we wouldn't be dividing by 0, we can just have this evaluate to 1 over x. So divide 1x. And then we need to close our if. And now if we run and we compute inverse of 4, we get what we want, but inverse of 0 produces an error, and we can click on the stop signs to see where this error came from. That's everything that I'll be stepping through with you. What remains is for you to write 3 functions, which will be the thing you turn in for this lab. So you should implement in the definition pane 3 different functions, and then you should save that with the floppy disk icon into a file called lab1.rkt, and that will be what you commit to your repository and push as your submission for this assignment.